capacity expressions. So first of all, we will try to understand the channel capacity expressions, understand what are the underlying assumptions behind the expressions, and from there we can try to understand the properties and what we can learn from the expressions. So in most of the literature, if you read through some of the technical papers, sometimes this degrees of freedom gain is referred to as the multiplexing gain. So how much we can multiplex signals from different users together at a given time. And then we will see later on that the degree of freedom is actually related to what we call as the dimensionality of the noiseless receive signal space. And from this dimensionality, we can identify how much data that we can multiplex together at a given time period. Okay, so this is the content. So basically we are going to focus on the first 2 points. The last 3 and 4 I put optional, so if you are interested in reading that more, you can explore at your own time. Okay, so if you recall the communications block diagram, we have source. Source is something that generates messages, something coming either from human, coming from the nature, coming from the machines, and so on and so forth. And then before the message is getting transmitted over the channel, it will be transformed first so that it will have a suitable form for the transmissions. So here we have the transmitter, we have the encoder source. So this typically happens just after the application layer. And then we have the encoder, which basically addresses the limitations of the channel. So this encoder concerns about removing the redundancy on the source. The second encoder is used to address the physical degradation of the channel. So if you talk about the channel coding, this actually refers to the second part of the encoded block. So channel coding is used to mitigate the, you can call it as a noise aspect of the channel. And then we have the modulations, because you want to transmit at a particular frequency with a particular characteristics, and then finally the transmitted signals will be transmitted over the channel, and at the reverse, the receiver will perform the opposite operations to what the transmitter has done, and then the received message will go to the intended target. So this is basically like a basic communications block diagram. Okay, so what we are going to assume in this lecture is that we are not going to talk about this, because this can take another lecture to deliver these 2 block diagrams. We are going to focus on the channel encoder, modulator. We are going to merge those 2 together. So actually when you do coding here, you can do coding using the QM symbols. So for example, like usually when we talk about coding applies on the binary sources, right? So let's say you have this, then you have repetition coding of length 3, then 0 will be repeated times, 1 will be repeated 2 times. So this is what we call as the binary channel coding. But when we talk about merging the role of these 2, we can actually further transform this into some kind of baseband modulation format. So for example, like if you use binary phase shift keying, then this 0 can be converted to -1, 1 can become 1 plus 1, and so on and so forth. So we basically, when we are saying that we are merging these 2 roles, we are doing the mapping directly from the source to the encoding at the modulation layer. So we don't really care much about the binary. Yeah. What we are going to assume is that we are going to focus on the discrete time representations, and it's at the baseband level. So we are not talking about the frequency here. We assume that the frequency is perfectly synchronized. We can easily demodulate from the passband signaling to the baseband level. Okay, so with that simplified communication setup, we have source, channel encoder, channel decoder, destination sync. So it's very simple model, right? So we have here source, for example, will emit the message M, then M will be transformed with one-to-one mapping by the channel encoder, so X, And then channel will introduce some distortion to X, will become Y. From Y, we try to infer what message was transmitted using the channel decoder with a certain rule, and then we will output M hat to the destination C. So what are the properties of those blocks? So the source generates a number of messages, M, 1, 2, capital M. Because it's not very informative, right? If you only have one message, there is no need to communicate. Right? So to make it a useful communications, we need to have a number of messages. Just like alphabet, right? We have ABC, right? If only one alphabet, then why bother to transmit, right? Everyone will know, right? With one alphabet. And then channel encoder, the outputs will be what we call as the code word. We do not mean X with the bold-faced font. And actually that X represents lang n code word. So we have lang n means X1 to Xn. And then the coded symbols are transmitted over the channels and will be corrupted by the noise, by distortion, including fading, and so on and so forth. And then we have the receive sequence, we call it as Y1 to Yn. And the channel decoder will use that sequence to infer what message was transmitted. Okay. And then we can actually, from that setup, we can define what we mean by the transmission rate. So transmission rate is defined by the ratio of log to M. So remember, M is the number of messages divided by N. So for example, if we have only 2 messages, binary messages, then we have log to M. So log to 2 is 1 bit. If we use N code word, this means that the rate is 1 over N. Because to transmit 1 bit, we need this long code word. So the unit for that is bits per channel use or bits per dimension. So sometimes you can also see like bits per second per hertz. So this is equivalent to the bits per channel use or bits per dimension. Why we have the channel use there? Because we are using the channels times, right? With lang n code word, we are using the channel n times. Transmit the signals.
Sir,
yes?
can you give examples of that equation?
Okay, so examples for this.
Yes.
So, okay, remember that from the previous slides, we have M messages, right? M messages means list of possible messages. So let's say 1 to M, which is M. So M can take any one of these, right? This will be decided by the source, which message will be transmitted to the channel. And then we have the source. Source will pick up this. So if we have, for example, binary messages. So what are the examples of binary messages?
1 and 0.
Yes, 1 and 0, but what are the physical examples of it?
Characters.
Sorry?
ASCII.
ASCII code. Okay, that may be a bit too long because that will involve the source. Tossing coin, right?
Yeah.
So suppose that okay, you have a brother or sister living far away, tossing a coin, and want to transmit that outcome of that tossing coin to you. So it's either head or tail, right? So binary, right? So in a way, like you have 2 possible messages. So the rate for that message is log to 2, so it's 1 bit, right? Because you can represent head or tail with 1 bit, right? And then if you use, let's say, repetition coding, so you will repeat, let's say, 3 times. So in this case, your N to represent that particular outcome will be 3. Will be 3 symbols, right?
So if the kind of dice, we have 6 possibilities.
Okay. Another example is for dice. We have 6 possible messages. 6 possible messages. 6 possible messages. And then if you want to represent that with a code word, then obviously 6 possible messages is log to 6 divided with the code word that you are trying to transmit over. So obviously 6 is not a good number because it's not multiplicative of 2, right? So we have a 2 to the power something fractional number instead of a whole number. Right? So, okay, is it clear? Yes.
So in this case, X is also modulated symbol.
Yes, modulated. So it's a combination. So okay, to give a real example is we have a coin, right? just some drawing. This is head and tail, right? So head tail can, let's say we call it 0 or 1, and then we, let's say, modulate using, not modulate, we encode using repetition codes combined with BPSK signaling, for example, 3 times. This will become -1, -1, -1. This will become -1, -1. So actually x will represent, let's say we are going to transit 0, then x will be this -1, -1, -1. In this case, n is 3. In this case, n is 3, m is 2, so log 2 is 1 over 3, right? So the rate is 1 over 3. Actually, you can take it from the intuition's point of view. Like, you need 3 time unit to just transmit 1 bit. So that's actually like the intuition expression. So I have to start with this because otherwise, if we talk about data rate, etc., then someone will have its own interpretation to data rate, right? So I try to limit that interpretations with the proper definition. And this actually, later on, you can see that it's connected to Shannon capacity. So, okay, good to go? Okay, so basically like, the questions in which Shannon, the one that make a breakthrough for digital communication, is can we achieve a strictly positive rate with error probability that goes to 0? That's the question. Because at the time it is not very clear. So in order to understand this, we will review some elements of Shannon information theory, and then we will use the MIMO communication. So, in order to study Shannon information theory, we have a couple of terms that we need to understand. So, first is what we call as entropy. Entropy. So, entropy, some people say also uncertainty. Uncertainty. So, you have a random variable called x, and what you do with this x is you are taking the probability of that x multiplied by log 2 of the probability, and you are summing over all x. So if you have these two possibilities, each with probability half, so the entropy of this will be 1. Just putting that. And then we have joint entropy. If we have more than one random variables. Conditional entropy if one random variable depends on another random variable. And then finally we have what we call as the mutual informations. Did Dr. Hoyle talk about this yesterday? Yeah? So I don't have to repeat this, okay? So mutual information is simply the difference between x and the conditional entropy of x given another random variable. So how do we see this? Okay? It's all maths, right? So usually it's quite not very intuitive to really put it in our head. Okay, so what we can see is like this, right? So we have source. Remember source. Source have, let's say, m possible messages, right? 1, 2, n, right? So suppose that all messages are equally probable. So this means that message 1 we have a probability of 1 over m being transmitted. Message m will have the probability of 1 over m of being transmitted. So in this case, if we do not have any channel, and we are just a receiver like observer, then we have the highest uncertainty, right? Because we cannot really differentiate which message will be transmitted. They are all equally probable. They have the same probability, so we cannot really one is more likely than the others, right? So as an observer, we have difficulty in getting a proper knowledge about what message has been generated by the source. Okay, so the purpose of the communications is actually to reduce this uncertainty. So we have channel, which basically will pick up one of these, And then what we observe is the one being produced by the channel, which has a direct relationship with one of these possible messages. So if we only have access to this source, so we have the highest uncertainty. We have Hx, we have the entropy of x only. But if we have the observation of y here, y is related to x somehow, then we are more confident, right, about what we are trying to get. So actually we have reduction in uncertainty. So that reduction is what we call as the mutual information. So it's actually, at this point, our entropy is Hx conditions on y, because we have access to y. So from y we can possibly infer x. And the difference between these two is actually the number of bits that are getting transmitted over the channel. The reductions on the uncertainty. So if we have a perfect channel, so anything transmitted by the channel will be delivered as it is. So in this case we have y equal to x, right? So what is this entropy? 0, right?
Yeah.
So all the bits coming here will be transmitted over. If we have a very bad channel where y is independent of x, what's going to happen with this? It's actually equal to hx, right? Because any knowledge of y will not help us to understand x. So hx minus hx, 0. So you cannot actually achieve a really good communication performance if you encounter such a channel. Okay. Question? So far so good.